So that is Olufemi Olorode. I think I got that right. And he is an assistant professor at the Louisiana State University. And he is here today to talk about numerical modeling of fractured unconventional oil and gas reservoirs. So Femi, the screen is yours. Please go ahead.
Thank you very much. Can you see my screen?
Yes, it is very good. Thank you.
Thank you. Hello, everyone. I'd like to start by thanking Cynthia for organizing this symposium and for the opportunity to talk about our work on the Shale module, which is one of the third-party modules in MRST. I am an assistant professor of petroleum engineering at LSU, and I'll be talking on numerical modeling of fractured unconventional oil and gas reservoirs. And by that, I mean shale gas, shale oil reservoirs. So shale oil and gas reservoirs are typically compositional, and they typically have lots of fractures. So they're typically naturally fractured. So the goal is to be able to model this type of system. So in the middle of the domain, we have the horizontal well, and then we have multiple fractures in clusters. We have groups of trees at each fracture stage. And in addition to that, we have the natural fractures. So today, there is no technology to determine the exact location, the size, the orientation, and the properties of all of the fractures in the domain. So our goal is not to model the exact location, which we don't have. The goal is to be able to create multiple stochastic realizations of these natural fractures so that we can quantify the effect of the uncertainty on production. So for that, we used another open source MATLAB package called EDFM, which I will talk about in the demo section. Here, I show the stereo net, and each point in the stereo net corresponds to the orientation of each of the fractures in the domain. I'm going to move quickly through this slide because these are the governing equations. This is for the water phase. The three terms are the accumulation term, flux term, and source or sink term. And we'll be modifying these in the demo section. So for the hydrocarbon components in the liquid and gas phases, the equation is similar. First term is also accumulation, second is flux term, this is the flux term, and this is the source or sink term that can be used to model the well. This is the Darcy equation for the velocity. So like I said, we will be using EDFM to model the stochastic fracture realizations. This is a simple code that generates those natural fractures in the first slide. And we wrote this function to process the points, which are basically the vertices of all the natural fractures. And then after processing, this is passed to MRST, precisely the HFM module for fracture modeling. I should mention the Shale module was developed based on the HFM and compositional modules to capture the natural fractures we have in shales and the tendency for shales to have compositional effects. So these fractures will be used in the HFM module, and then we extended the HFM module to do pEDFM, which I'll talk about shortly. In these functions, there is DIR, which is the deep direction, and there is deep, which is the angle between the horizontal and the fracture. And then so the deep and the deep directions are used in EDFM to completely specify the orientation of all of the natural fractures. This is a quick summary of EDFM or HFM. They mean the same thing. It uses the concept of non-neighboring connections to allow the fractures in the domain to communicate with the matrix. So we have three main types of non-neighboring connections. First is matrix fracture, NNC. So this fracture communicates with the matrix which hosts it. And that matrix which hosts the fracture cell is called the host matrix cell. intersecting fracture NNC, so fractures or fracture cells that are part of two different fracture planes. Those we will need some non-neighboring connectivity to allow them communicate. And the last here is fracture segment NNC, which will be fracture cells that are part of the same fracture plane. So technically, these are not really non-neighboring connections, right? Because they are neighbors. And MRST will handle these just like it handles two neighboring matrix cells. And then you easily calculate the transmissibility. So these two are the main NNCs we need to worry about in HFM. And I should say the matrix cells are meshed independently of the fracture cells. And what that does is it allows the mesh for the fracture to be, basically the mesh for the domain doesn't have to conform to the orientation of all of the natural fractures in the domain. And that's why EDFM is fast and has been used a lot. So like I said, we use QNNC to implement EDFM, which is the non-neighboring flux. And this is the governing equation. When there are no fractures, we add QNNC to incorporate the flux between the matrix and the fracture. And this is the expression for the QNNC. And it basically looks like the matrix fracture transfer term in dual permeability model. So we group Ka and D together, and that's your transmissibility. And depending on the type of NNC, we have different equations for the transmissibility. So the matrix fracture NNC, these are the equations for Ka and D. For the intersecting fracture NNC, these are the corresponding equations. And these two references provide more details on EDFM. So in 2017, Tin and others came up with the projection-based EDFM, which basically adds what is called projection cells. So a fracture in a host matrix cell projects an area onto one projection cell in each direction. So in each direction, meaning in the X and Y direction in 2D, we need one projection cell each. And that algorithm to figure out the projection cell is some geometrical calculations, is fairly complex. And our contribution in the Shale module was to extend this algorithm to 3D. So we have a 3D algorithm that determines the projection matrix cells. And then all we need to do is to add two more NNCs to implement pEDFM. And that will be the NNC between the projection cell in orange and the fracture, and also between the projection cell and the host cell. And those are the equations for those two transmissibilities. So this is the paper where we implemented the 3D pEDFM algorithm. And this example was based on an example in the Tin et al.'s 2017 paper, where they have a domain, Dirichlet boundary conditions on the left and right, high pressure on the left, low pressure on the right, so that the pressure basically diffuses through the system. Top and bottom, no flow boundary conditions. And in the middle of the domain, we have two intersecting fractures. And in the first case, which is the case on this slide, the fractures are modeled as high conductivity fractures. On the next slide, we'll show the fractures being modeled as low conductivity fractures. And the question is EDFM applicable in both cases? So we created an explicit model, which basically means very fine grid blocks. And the smallest grid block is the thickness, the width of the smallest grid block is equal to the aperture of the fracture. So we have cells for each of the fracture segments, and that will be the reference solution. pEDFM model is able to replicate that with coarser grids. EDFM also does the same job. So pEDFM doesn't really add much when the conductivity of the fractures are high. Here we show the results, the pressure profile still, but for a line drawn from this point through the fractures to the end. So we grab variation of the pressure along that line, and that's what is plotted here. We do the same thing at low conductivity. Same setup, only difference is conductivity of the fracture in the middle is now very low. And then we want to figure out what the results will look like. This is the reference solution. pEDFM matches that, but EDFM doesn't see that there are actually sealing fractures in the middle of the domain. So that is the limitation of EDFM, and that's why we need to figure out the projection cells and account for low conductivity fractures accurately. And these also shows the same thing. So reference solution in black, red pretty much follows the trend, which is the pEDFM, and EDFM doesn't see it. So here we see the effect of low conductivity fractures on the pressure profile. The next question is, what is the effect of these low conductivity fractures on production? So for that, we created a different case. In the middle, we have hydraulic fracture, and we have a well connected to the hydraulic fracture. And we have two fractures to the left and to the right, and we made them sealing so that it will curtail the flow of fluids towards the well. And then we want to figure out if pEDFM, EDFM is able to capture that expected behavior. So this is the reference solution. pEDFM looks like that, so it looks like it's doing a good job. EDFM doesn't see the sealing fracture, so the pressure profile just diffuses through the domain like the sealing fractures do not exist. And what is the effect of these on production? This is the result. So EDFM, which is the blue dotted line, overestimates production, but pEDFM matches the reference solution. In the demo session, I'm going to talk about this. This is the same mesh from the beginning, where we're able to simulate it for 30 years. This is a pressure profile we created using ParaView after 30 years of production. Oil saturation profile, water saturation profile at the same time. Methane, ethane, just two out of the different compositions to show that it's a compositional simulation, and we have the natural fractures in there. And this shows the error introduced by not accounting for the sealing fracture. So some of the fractures were said to be sealing, half of them were sealing, half of them were conductive. And this is the effect on production. And so EDFM overestimates production. And this is the type of error we don't like in petroleum engineering, right? Because it could mean you will commit more financial resources to the project, and then after development, you realize production doesn't meet expectation. So in addition to the 3D pEDFM algorithm in the Shale module, we also created some examples to show how you could incorporate specific physical mechanisms that are unique to shale gas. And in the paper, we showed, in the book chapter we have in the advanced MRST book, we show sorption modeling, diffusion modeling, and modeling of a stress-dependent permeability. So definitely I don't have the time to go through all three, but here I'll show how we model sorption. And that means we'll go into how we modify the governing equations for compositional simulation to incorporate additional physical mechanisms that are unique to shale. So this is the sorption. This is the Langmuir isotherm. It can be written in different forms. Here we're showing it in terms of density so that we can use SI units, and it's compatible with all the other variables in the governing equation. So this is the sorbed density. This is the maximum sorbed amount in terms of density. And this is the reservoir pressure. PL is called the Langmuir pressure. And we will see what these two model parameters mean. So those are the only two model parameters, ρSL and PL. So this is the plot of ρS against P. It tends to flatten out at high pressures. And then the maximum value it flattens out to is the ρSL. And we find half of that. So half of ρSL takes us to this horizontal red line, and we project that to the blue line, and then back down to the pressure axis, and that is the Langmuir pressure. So the definition of the Langmuir pressure is is the pressure at half of the maximum sorbed amount. This is the governing equation, and all we have done is to add this term to the accumulation term, right? And this is some flag that indicates whether you have a matrix cell or a fracture cell. So it's 1 for the matrix, 0 for the fracture. Why? Because we have sorption in the matrix. The fracture could be a crack, right? An open crack. So nothing is sorbed because there is no matrix. There's no grain volume. So it's 1 or 0 depending on whether it's matrix or fracture. And that automatically takes care of removing sorption in the fracture. 1 minus phi is basically grain volume divided by bulk volume. And here we show the sorbed amount in density for each hydrocarbon component. This is for the entire hydrocarbon phase. So we need the extended Langmuir isotherm, which is shown here. And that's what we implemented in the compositional module. And we'll be talking about that in details in the demo section. Here I show, instead of using make rock function, we use make shale rock. And the only difference is to incorporate that delta S, the flag 0 or 1, to determine whether it's a matrix or a fracture. If you want to model sorption, you add this line. If you don't want to model sorption, you delete this line. And then it works like a normal porous medium without fractures. And this modification is made in the setup EDFM operators or setup TPFA operators. And this is where we store in the S operator, that's where we stored the discrete divergence operations, the discrete gradient operators were stored in S. So we decided to store this in there so that it is available within the equations variable natural function where the governing equations will be implemented. So this is where it's calculated and stored in the S operator, and then we'll use it in the equations natural variables operation. What is this? This is from the get compositional fluid function. And that's where we specify the parameters of the Langmuir isotherm so that it's available for use in the governing equation. Here, we only focus on computing this term in the denominator. Why? Because for every composition I, for every hydrocarbon component I, this summation never changes. So we want to calculate it just once. So in the loop, we calculate it 1 time, and then we will use it for each hydrocarbon component in another for loop. So like I said, this is from equations variables natural, and this is where we calculate this term that gets added to the accumulation term in the governing equation. I've ignored the other terms in the equation here. So this is the standard accumulation term, which is this. And then this is what we have added to the function only if you want sorption active. That's why we have the condition in the function. So we're using the sum of the iso, which is this term that I showed on the previous slide. And that's how we modify the governing equation. And now the simulator accounts for sorption. I'll show these results in the demo section. This is the model. We simulate multiple fractures, and the results with and without absorption are shown here. And with that, I'll go to the demo section. How am I doing on time? 20 minutes. So this is our Shale module. What we have added recently is this folder, which has all the code for all the figures that were in this 3D pEDFM paper. The codes to generate all the examples in the book chapter, part of the advanced MRST book, is here under examples. And then the HFM functions are the functions from the HFM module that we have extended. The compositional functions are the functions from the compositional module we have extended. And very briefly, I'll show how to use EDFM. So we are not able to distribute EDFM together with our Shale module because everyone needs to send an email to the author of the package, and then he sends you the zip file, and then you unzip it and put it inside your Shale module. And right after that, you can right click on it and add to path. And that will make it available. So you will be able to change the parameters of these natural fractures and then have the simulation adjust with the changing parameters. Otherwise, you'll be using the realization we have created. So this is how the EDFM works. You have these functions that I talked about before. We can run it. It creates the stereo net here. It creates the figure with the mesh and the fractures as shown here. 2 fracture sets corresponding to set 1 and set 2. You can have as many as you want. And then here we show the stereo net. Each point, like I said, represents the orientation of each of the fractures. And that basically summarizes how to generate all the natural fractures. For those cases, the validation cases that show that pEDFM captures the effect of the salient fractures in the middle of the domain, they are here. This is at high fracture conductivity. This is at low fracture conductivity. The code is almost identical. Only difference is the fracture permeability. So that's how we control the fracture conductivity, and we kept the aperture the same. So these are the functions that were modified in HFM. We just added a shell to it, and we incorporate some parameters we need, like the unit vector and stuff. We store those in the grid. And then in our function, this is the function that does the 3D projection for pEDFM, just one function. So the difference in your MATLAB script between the EDFM code and the pEDFM code is just 2 functions. This function which we created to identify the projection cell, and instead of calling the setup EDFM operators, we will use the setup pEDFM operators, which I'm looking for right now. Right here. So we use setup pEDFM operators in pEDFM, and these are the results that I showed before. And all of this is available on GitHub. You can clone it and then reproduce those results. The last example I'll have enough time to talk about is the sorption case. Similar to that, we call those same functions. This is the make shale rock that has the delta S that is 0 or 1, depending on whether it's fracture or matrix cells. We can set the properties of each of the fractures. We can use stochastic distribution for these porosities, permeability, and aperture. So it changes. I just talked about these modifications to the HFM module. This is our projection matrix function, and we can plot the grid that has both the mesh and the hydraulic fractures. This is set up pEDFM operators for pEDFM, and that is set up EDFM operators. And the rest is pretty standard HFM code. So we've just combined HFM with compositional simulation and added projection-based modeling. I think I'd like to stop at this point, so I have enough time to take any questions. Thank you.
Thank you very much, Femi, for a very interesting talk. I think this is a very nice contribution, and there is certainly a growing interest, I'd say, in fracture simulations in MRST. So this was really nice to see. And as you mentioned, there is also a chapter on this work in the upcoming book on advanced modeling with the MATLAB Reservoir Simulation Toolbox. So we have a few questions in Zulip. Remember that you can still ask questions there if you use the stream WE3. And I hope, Femi, that you're able to also answer questions in that stream, not just now, but also throughout the symposium and hopefully also for the coming week.
Absolutely.
Perfect. I think we have time for a few questions. This first one is from Daniel Wang. And he asks, as you can see on the screen, have you explored whether the module could be used for coal seam gas production modeling?
I've never tried it, but I know they both use the same Langmuir isotherm, so I see no reason why not.
Very good. And then the next question from Ehsan Ranai. Thanks for sharing your great work. Apart from obviously computational costs, could you please comment on the benefits and limitations of EDFM in comparison with dual continuum technique already available in MRST for field scale applications?
Thank you for the question. So the main difference is that the dual continuum model assumes that you have a dense fracture network, and then the properties of the fractures are more or less homogeneous throughout the domain. So in unconventionals, we don't have that. We don't see as much of a dense fracture network. Some fractures are much longer than others, and the fracture properties could be very different. In those cases, that's where it's important to be able to account for each of the fractures independently. So EDFM will account for each of the fractures independently, whereas the dual continuum basically homogenizes the fracture throughout the domain. So that would be the limitation in dual continuum. If you have lots of fractures, dual continuum will be faster than EDFM because you have to account for each of the fractures in EDFM.
There may also be, I don't know, but maybe a possibility to combine the two types of approaches so that you can take parts of the domain with one formulation and other parts with the EDFM.
Yes, and I've seen some papers addressing that. So yeah, that will be some natural extensions to this work.
Very good. Next question from Nikolai Andrianov. Great work, thanks. Have noticed that you use Parpool. Would it run without the parallel computing toolbox?
I believe it will run without the parallel computing toolbox, but it will only use one processor. And we didn't do anything about this. We basically used what was already in the HFM module. So this parallel computing was done in the HFM module.
So there is the parallel computing toolbox is very convenient, but if you write the par for loop using the parallel computing toolbox and you don't have the toolbox available, it will just default to a regular for loop. So if that's the case, then it will run. It's just going, as you say, to be quite slow because it doesn't run anything in parallel.
Yeah.
Yes.
Yes.
Okay, I think that is it for now. Thank you again very much for a very nice presentation.